That's it, man. Game over, man. It's game over.
No, God, please, no! No! No!
I am very disappointed!
If you judge Spring AI 2 only by the number of new features, you can easily reach the wrong but very sad conclusion. It's understandable, we waited for more than a year, then the release was postponed and delayed again. And all of that for only 13% new features, and some of those are just new model support. So not even 10% real new functionality. No growth means stagnation and game over for the framework. But the truth is, it's exactly the opposite. For Spring AI, it only means that the project has finally been taken seriously. For over 2 years, Spring AI has been an official Spring project, but with its rapid growth, there was never enough time to even define the common standards. Builders and chain patterns mixed together with Java beans and mutable objects. Eventually, it reached a breaking point. So the release was delayed to clean up the project and set a new baseline. And this chart just emphasizes how important this project has become. So if the Spring team is investing this much effort into making Spring AI the default choice for the JVM developers building AI applications, then it deserves more than just one talk. That's why I want to start a whole series, each episode focused on one key mechanism of Spring AI and his friends, highlighting what changed in version 2 along the way. If you enjoyed today's episode, please hit like and share it around. For me, that's the only real feedback I get. If I see people are watching and enjoying it, I know it makes sense to keep going. I also launched a Telegram channel for this series. Subscribe there for the next episodes, code links and other useful materials. Hello, I'm Evgeny Borisov, over 25 years of Java experience, 15 years as an international speaker, Java rockstar, and the last few years I focus on building agentic systems. So, the hero of today's episode is ChatClient. This bean is our gateway to speaking with almost any model, including the local ones. ChatClient, where our beautiful deterministic code ends and begins the mystical chaos of the LLM. We pass our prompt to the ChatClient, it adds certain settings to it, and then sends the request to the LLM through a transport layer, HTTP in our case. Today we are going to look at how these settings affect the quality of model responses. And to understand how the model thinks while building an answer, I'll show you how to read Logprobs, its raw model thoughts, and turn them into useful logs. But before we start tuning the ChatClient configuration for better answers, let's take a moment to get everyone on the same page about how the model actually thinks.
Hey buddy, you got a dead cat in there or what?
Fuck you, asshole.
Attention! Terminator doesn't understand the text. Model sees only a sequence of tokens. To simplify, imagine that question is a token and the answer is a token. To find the most suitable token for an answer, the model calculates a selection score for every token in its vocabulary. Not by meaning, but using a formula learned from billions of examples showing how each token's likelihood depends on context. And then comes the roulette. The higher the token score, the bigger its slice, so the greater its chance to be selected. In reality, a token is not a phrase. It can be a word, part of a word, letter, or any symbol. The model builds the whole answer one token at a time. Each time it looks again on the full context, your request plus a part already generated, and scores the next token again until the roulette picks the end of turn token. Let's see how this works in practice. Since today we are talking about ChatClient, we will focus at the Spring AI starter dependency and its version, the ChatClient configuration, and write the code that uses it. And in Docker we'll start Ollama, container to run models locally, so we don't have to worry about token costs or depend on vendors with their restrictions. I'm going to work with IntelliJ IDEA, my favorite IDE for more than 20 years. So this is my Docker Compose with Ollama latest and its external port configuration, volume, and one important life hack. By default, Ollama works on CPU. If you want to allow GPU usage, you need to provide this block with amount of cores allowed. It will improve the performance dramatically. And this is a model I'm gonna pull. It's gamma-free Google model with 260k tokens of vocabulary, not context window, vocabulary. And here's my POM. The only dependency AI related I have here is Ollama starter, but it has a new baseline, Spring AI 2, which requires at least Spring Boot 4, Java 25, and it may apply other libraries as well. For example, Jackson I'm not using here, it's only my transitive dependencies, but it still need be more than version 3. Now let's see the main configuration. Nothing about AI meanwhile, just simple Spring Boot application, and the only bin I have here comes from a web starter, since I want my chat client to use HTTP when talking to Ollama, and the model might get stuck. I want some reasonable timeout for my request factory and configure with it the builder of my REST client. And in the main method, after the context is created, there is a lookup for non-existent bin, AI Terminator service. And we try 10 times to call his non-existent method, finish the phrase, I'll be, try to guess what I suppose it should answer. So let's try to implement it. In order to create non-existing class, we can put here the cursor ... and I want to solve it is create a class, but actually it should be a service. So let's mark it with this AIService annotation. And as it needs to use ChatClient to communicate with Ollama in order to complete the sentence, I'll try directly inject the ChatClient bin here. And let's see if this one exists in the context, and IntelliJ says no, could not auto-wire, no bins of this type. And another warning from IntelliJ says field injection is not recommended. So let's try to see if we will use the constructor injection, but still we have the same problem because this bin doesn't exist. And let me check if I'll use the Lombok if IntelliJ is smart enough. And yes, it understands still that the injection exists, but okay. If ChatClient doesn't come to me, I will declare it by myself. I will type just bin and type should be ChatClient. Part of the new baseline of Spring AI 2 is immutable object. As a result, cherchez le builder. Look for the appropriate builder. So let's see, maybe we have some ChatClient builder, and we do. If we will try to put null here, we will see that IntelliJ warns us that it's prohibited as it knows new Java feature, JSpecify. And JSpecify is used by Spring AI since version 2. You can see that most of the methods says if it's can be nullable or not. Now let's go back to ChatClient. So if we must provide something here, let's try to look, maybe we have chat model, and yes, IntelliJ says we have such a bin in a context somewhere. Let's see where it is configured. So I'll click this magic button to drill down into Ollama configuration class, and its jar is here because of the Ollama starter. This one is after configuration, so Spring Boot will find it in the bootstrap, and in case all the conditions are true, it will be activated. Then it will enable Ollama chat properties, and here we can configure the name of the model, numPredict, the maximum number of tokens per request, and other useful parameters. Ollama chat properties marked by configuration properties, so all the values will come from the environment with this prefix. And if we will search for this one, double shift, we will find the exact location where it can be configured. So this is my application properties in my resources, and here is the parameters. I, for example, configure the numPredict to be 13, my gamma, and we can see the same parameters we saw before. And this is my URL. Remember the port I exposed via Docker Compose. IntelliJ can help me to see where these parameters are used, and now I am exactly in the same Ollama chat properties, and we saw it will be configured by the setter with Spring Boot in order to inject the value from the environment. And if we will go to auto-wired candidates, now we're back in the same Ollama chat after configuration, and these properties will be used here to be taken to Ollama chat options, and this chat model bean will be injected to our configuration. What else we can configure for ChatClient? We can override the application properties we saw previously. Here we need the chat options, so again it will be some builder, and for example, yes, I want max tokens to be 40. And now you see IntelliJ hints me to make the build like it was in Spring AI 1. Now we need to provide just the options builder, and then Spring AI will merge it with additional values, and then it will build the immutable object. And finally, I want to configure the system prompt. It should be one word. Remember, we in order to make it easier to understand how the model thinks, we want to say your command is to complete the sentence with one word only. Build, and then double dot, return, yes, insert return. Okay, we need to finish the phrase I'll be. So now let's use the chat client. Here is my user message. I need to return chat client dot prompt. My prompt will be user message. We can use streaming if we want, but it will be very difficult to understand and to debug the parameters I want to show you. So I will not use stream, I will use call, and then you can get the content, or you can take some metadata from there. If you will want to see the implementation, it takes the chat response and then it extracts from the chat response the result, get output, and then get text or else null. So it's exactly to save all this chain, I can just call the content method, and actually I'm done. Let's run this. Not even one, I'll be back. The token there wins every time. Sometimes it comes with a dot, sometimes without. To understand more, we need to ask Ollama for Logprobs and see the alternative tokens with their scores. We can curl the same URL directly, just like Spring AI does under the hood, with the same request parameters, the model name, stream, our prompt, other configuration, but I want Logprobs, so it will be true. And since I don't need the whole model vocabulary, I'll limit to the top 10. Now the response has not only the model answer, but also 10 alternative tokens with their scores. It's hard to understand and compare them without normalization, so let's make them readable and put them into the log. But Spring AI doesn't support Logprobs. ChatGPT, Claude, all of them told me this task is impossible. Even if I will be able to add the Logprob parameters to the request, when the response will come, Spring AI will filter it out. But still there is a way how to do that. Let's go back to our main configuration. And here I want to add the request interceptor. Oh, IntelliJ is right. I will take my class, which takes in the constructor amount of Logprobs we want to log. And in the only method I need to implement, I have the request and I have the body. So first of all, I need to check if the URL is correct. Then I'm reading the body with Jackson to JSON. Then I'm adding the Logprob parameters, converting it back to the byte array. And then I'm executing the request. And when the response will come, before I will send it back to the application, I have a chance to print it, and I'm doing the normalization inside my print table method. So let's run it now. So here is the response, and now we can see here is the token which was chosen, and we have the original Logprob. After normalization, this one takes almost 100%, and the back is here in the last place. Regarding the dot, sometimes we can see the dot is printed out, and sometimes we see that there is no dot. The reason is because the token end of term has only 42%, so it's half and a half. Sometimes there is end of term before the dot, sometimes it comes after. Now let's increase the chances of I'll be back. Let's add some context to the system prompt. Instead of using this prompt, I will change the one word prompt to this one. It's exactly the same complete with one word only, but I'm adding you are the Terminator. And let's run it again. Let's take a look. Now we are talking. See how just a couple of words can change the whole context. The same tokens got completely different scores. Back jumped from almost 0 to almost 100, and the next 4 tokens are different as well. Now let's see how the other ChatClient settings affect the result. But let's change the Terminator story first. In the previous examples, the model's choice was too obvious. The demo goes flat if one token takes almost the whole roulette wheel. So let's take an unusual situation. Now we have a cliffhanger. What's he gonna do? That's the exact question I put into my system prompt after describing the setup of the blockbuster you just saw. Let's see how the Terminator completes his famous line in this new FIFA context. And I'll switch the logger to more advanced one for deeper insight into the power of ChatClient configuration. Let's run this. Let's see the result. Revenge. One more revenge. Eliminate. It seems like nothing good is waiting for the referee. About the logger. It takes into account 3 additional parameters we can configure, top K, top P, but we will start with the temperature. Remember this? Mathematically, temperature can go from 0 to infinity. But for most frontier models, temperature should be between 0 and 2 and will be ignored if it's out of range. At temperature 1 doesn't change the roulette at all. This is the most common default, by the way. But when temperature goes below 1, the distribution gets sharper, strong tokens get stronger, weak tokens get weaker, and teeny ones start to disappear. At a temperature 0, only one option is left. No roulette needed at all. The best token is always picked. So you might expect the same answer every time in this case, but it's not guaranteed. These calculations run in parallel, and a different order can produce slightly different results because of rounding. I saw this myself. The same prompt, same LLM and model produces slightly different scores on the CPU and GPU, for example. So if 2 tokens are very close, even a teeny difference can make the second one come first. And then temperature above 1 have the opposite effect. The gap between strong and weak tokens start to shrink like under socialism. Strong tokens share more and more of their roulette slice with weaker ones. The higher the temperature, the more equal the slices become. The probability order doesn't change, but at very high temperatures, we finally reach communism. Everyone is equal. So higher temperature makes the model more creative, while it stays in a reasonable range, around 2, let's say. But if we push it too high, we get pure bullshit. Tokens we never saw before, because their chances were too small, now show up as often as normal ones. Now let's see the logger again. What do we see in this table? The model still answers with one word, but it's split into several tokens, so you can see that the token can be just part of a word. For each token, we see options considered and their probabilities before and after temperature. By the way, can you guess the temperature? Here is the hint. The opposite of socialism. Strong tokens get stronger and weak tokens get weaker, but not too much. So the temperature is below 1, but we never configured it. And my logarithm line at a temperature 1, token re would keep its original 75% of probability and would appear only 7 or 8 times out of 10. Here it appeared 9. So the answer, temperature, is 0.8 because it's Ollama default. So it all makes sense. Now, if we want maximum determinism, let's set the temperature to 0 and see if all 10 answers will be revenge. I could set the temperature in application properties, but I did it here in ChatClient bin configuration. The run is completed. Let's see the results. Now it is always revenge, and the final probability of the winner is always 100. At a temperature 0, the strongest token takes the whole pie from the others, the rest are removed. So in this scenario, the roulette is out of the game. Now let's try temperature of 2. Temperature 2. Let's see what Terminator will answer. Terminate 1 token, execute 1 token, revenge, retain, react, revenge again, revenge, eliminate. Revenge is still here, but not the star anymore. No surprise. Token re started at 75% as expected, same prompt, same context, so the original probability should stay the same. At temperature 0.8, it went up to 85, if you remember. Now, at temperature 2, it drops to 43, and elim jumps to 15.6. So, bottom line. Temperature 2, bonjour socialisme. Strong tokens get weaker, weak tokens get stronger. So the roulette slices become more equal. Now let's see if Terminator leaves the meaning zone at temperature 3. And at the same time, let's see new parameter, top K. The top K parameter sets how many top tokens are on the wheel. Ollama's default is 40. GPT, Claude and others use even higher default. If FIFA used the same approach, the round of 32 would look like this. And for semi-final, top K is 4, would look like this. We set top K to 1, so just like temperature 0, the wheel is out of the game. The top token gets 100, even if it's slightly above the next one. I cross out filter tokens in red, as in my Ollama pipeline, top K is applied first. With only 1 token left, temperature has no effect. We see only one number is here and it's always 100, so answer is always revenge. Before talking about the next parameter, let me show you how the chat client can be configured dynamically, in case we want that our method will take temperature as additional parameter. For example, we will provide this temperature here in order to change the method ... and double the second parameter, and let's go, we can press Ctrl B here. Now, in order to use this double we receive, let's say it's temperature T, we have an options here. So again, we will look for some chat options builder, chat options builder, and we can set the temperature to T like IntelliJ suggests. But we don't need to do the build. It's exactly, again, the same difference between Spring AI 2 and 1. So if we will run it again, we're supposed to see that the output will be exactly the same. Doesn't matter, right, where we set the temperature. But it seems like it does make difference. We can see very strange answers. It's sometimes, again, revenge. But it can be recalibrate or execute, overwrite. So it seems like temperature 3 is really working, and we can see that the top K is 0. So it's like we didn't set it at all. What actually happened? So the reason is that in case you will override the temperature or any other ChatClient configuration calling the options method, you will totally remove the previous ChatClient options, and the new one will be merged with only the default values from the application properties. So for example, if I will set the top K in application properties, you will see it will still take an effect. But in case it is configured in the ChatClient bin configuration, all these options will be removed in case we use the options method. So what was the right solution for Spring AI 1 and for Spring AI 2? Let's see the difference. In Spring AI 1, you couldn't extract the chat options from ChatClient, so you was needed to store them somewhere, and when you want to override one of the properties or several, in order to do that you need to take a copy of your default options to override the parameters you want to override, and then the merged options you would provide here. If you don't want to merge chat options by yourself, just don't use this method since Spring AI 2. Instead of that, we can create new chat options object, fill it with needed values, and then instead of using the prompt implementation which takes only the content, which is user message, we can provide here the whole prompt which will take user message as a content and the options I prepared before. And the merge will happen inside. So the implementation of this prompt method was in Spring AI 1, but what changed, if you want to see the implementation, tap ... and go to implementation. And the new thing is combine with method which exists since Spring AI 2, and the merge happens inside. Now before I'll check, let's change top K to value 2, and the temperature will remove from here as we configured it in the finish phrase method. Now let's see the combination of top K2 and temperature 3 and see if it really helped. Revenge, 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 rebuild, rebuild, revenge. Now we can see it works as expected. Top K is 2, all other tokens are crossed out before temperature even applied, and only the remaining 2 tokens get adjusted by temperature and normalized back to 100. See? 66, 33, well, 100. And temperature 3 is clearly applied. Look how much the probabilities changes for these 2 tokens. But we still don't get much variety in the answers because the model choice is limited to only 2 tokens. Now let's see the last parameter for today, top P. If top K is about quantity, top P is about quality. Top P06, which I set here, means we keep the best tokens until their total score reaches 60%. But first, top K leaves 4 tokens as I set it to 4. Next, temperature is applied to the survivors only. I set the temperature to 10 just for fun, but at least you can see how much the probabilities of the tokens that survived top K change from their original values. Then top P is applied. Considering the new probability scores affected by the temperature in the previous phase, the first 3 tokens already exceeds in total our top P limit of 60%. So the rest are removed. I cross them out in blue. So in the end, only 3 tokens are left for the wheel, and their total score is below 100, so they are normalized again. That gives us the third and final score. First score was the initial probability, then after temperature was applied, and after final normalization. Here is another example. Let's look on the token G, which won round 3. The token G had such a high initial score that it not only survived top K, but still remained above 95% even after temperature of 10 was applied to it. It alone exceeds the top P threshold, and as it's the only token left after normalization, it takes 100% of the wheel. Top P defaults to 0.9 in Ollama and 1 in the OpenAI API. Top P1 means filter nothing, as we consider all 100% of options we have. Let's summarize the whole flow. First, the model scores every token in its vocabulary based on the current context. Remember how adding Terminator to the system prompt dramatically changed the probability of token back? I'll be back instead of I'll be there. Same tokens, different context, different scores. After each token is scored, top K is applied, followed by top P. If more than one token still remains, they go onto the roulette wheel for sampling. Each token's final probability determines the size of its slice, so its chance of being selected. Temperature can appear at different stages, depending on the runtime you use. My runtime is Ollama, and as you saw, it applies temperature after top K, but before top P. In Hugging Face, temperature is part of the formula that calculates the initial scores, so it's applied first, even before top K. In Llama CPP, temperature is applied last. So the same model with the same prompt can produce different results in different runtimes. I hope you enjoyed today's episode. There are still plenty of Spring AI 2 topics to explore: RAG, MCP, agentic systems, and much more. All the code from today's episode will be available through my Telegram channel created specifically for this series. I read every comment there, so your feedback can influence what comes next. See you on the next episode.
I need your like, your share, and your subscription. And give your mother a kiss from me.